Indicators are organic molecules that change color as the pH of a solution changes. They are generally weak acids, or sometimes they're weak bases, but they are organic molecules with color, and some change color at low pHs, some change color at high pHs, but they all end up changing from one color to another over about a 1 to 2 pH range. We use indicators to tell us when we're getting near to a particular point in our titration between an acid and a base, and the point at which the indicator changes color is called its endpoint. Indicators are colorful organic molecules, usually weak acids or weak bases, that change color as the pH of a solution changes. The point at which the indicator changes color is called the endpoint of the indicator. And when we're choosing indicators, when we're titrating an acid-base solution, we want to choose an indicator whose color change, or endpoint, is bracketing the equivalence point of the acid-base titration. That way we can identify ahead of time where the color change occurs, and that tells us to slow down and start adding drop-wise solutions so that we can get a 1-drop drastic pH change, so that we get a nice steep line on our titration curve. This is a chart of a variety of indicators that we have. This chart is in your book. Some of these indicators we have, some we don't. The indicators that we have and we use frequently, actually the indicator that we've already used, one of them is bromothymol blue. This is a list of indicators in your book. This list of indicators is in your book. Some of these indicators we've already used. For example, we used crystal violet when we were doing the equilibrium lab. You've used bromophenol blue in another lab. In the antacid lab, we used bromothymol blue, and you may have in your first year chemistry class used phenolphthalein. That tends to be an easy to use and easy to see color change indicator. Maybe we used methyl violet instead of crystal violet. Anyway, so as you can see, the way that these indicators are arranged is as the pH of their endpoint increases, we're moving down the chart. So they're not in any alphabetical order, they're more in pH endpoint order. Some indicators, as you can see with creosol red and with thymol blue and with alizarin, have multiple, in this case 2 endpoints, and so they'll change from one color to another at one pH, and then they change to a brand new color at the second pH. So in the lab that we're going to be doing, where we're going to be titrating a strong acid with a strong base and then a weak acid with a strong base, it's going to be your job to choose which indicator is going to be most useful to help you identify when you're nearing the end point and therefore the equivalence point for your titration. Ideally, you want to aim for 1 drop of base to cause the pH spike to be vertical and get a nice clear vertical line on your titration chart. Okay, let's take a look at a titration and indicators problem here. So if we're looking at this titration graph, you should be able to identify whether you're titrating an acid or a base. Actually, if you look at the labels on the axes, it tells you that you're adding 0.1 molar sodium hydroxide, so you must be titrating an acid with a base. So let's see if we can identify these various points on the graph. First of all, the equivalence point, where would that be? Remember, the equivalence point is where the hydrogen ion concentration equals the hydroxide ion concentration, and so you're neutralizing them, and so hopefully you came up with point X. The region of maximum buffering. When we're looking at region of maximum buffering, remember we're looking at the relatively flat portion of our graph before we get to the equivalence point, so it's going to be in this region right here. So maximum buffering is going to be right there. Where does the pH equal the pK? Well, if we're titrating with a weak acid, with this base, here is our volume at equivalence, so half of that, or right here, is going to be our half volume. That's where the hydrogen ion concentration equals the acid concentration. And so our choice for that is going to be letter V. So for where does the pH depend on just the acid concentration? Well, does it depend on the acid concentration anywhere? Where did I get this question? Well, where I have only acid and no base, the only place that occurs is at a volume of 0 sodium hydroxide. So that's going to be right there. The pH depending only on the anion. Well, where does the pH depend only on the anion? Since we're titrating with a weak acid, the anion from the weak acid is going to, as it's produced, react with water. And so the place where the pH depends only on the concentration of the anion is, again, going to be at the equivalence point. So that would be position X. So if I look at the chart from the previous slide, which of the indicators would be best to use? Well, the equivalence point pH is about 9. So let's go back to our previous chart. We need something that changes around pH 9. So pH 9, that would be orthocreosulfathaline, phenolphthalein. Really are the only ones that bracket 9. Phenolphthalein is really easy. The color change for phenolphthalein is from colorless to hot pink. That's pretty easy to see. Orthocreosulfathaline, I've never used before. So that looks like it does about the same thing. So either of those would be good choices to use. We have phenolphthalein in the lab, so that'd be the one I'd pick if I had to choose one for this particular titration.